Today we're going to look at something, and tomorrow will be a good day for a work day. So you got the assignment for simplifying complex fractions, where you got fractions divided by fractions. Not a big deal, really. That's a pretty lightweight one. This one takes a little practice. It's not like it's such a terrible thing, but it's a process that takes a little practice. So we're going to talk about dividing polynomials. There's a couple different ways we'll do this. Today we're going to talk about polynomial long division. This is the technique that always works. There is a shortcut that works in some cases that we'll talk about on Wednesday called synthetic division. It's great. It's super handy when it works, but it doesn't always work. And we'll talk about when to use it and when not to on Wednesday. Okay, so first of all, let's start easy. What if we divide a polynomial by a monomial? So something like this. We got a polynomial in the numerator, and the bottom I have a monomial. How would you deal with that one? What do you think? What's your intuition tell you about that?
I'll factor out the numerator. Factor out the 3, right?
Factor out, so factor, okay, so this is one where we're not actually going to be doing a lot of factoring here. Okay, this is with division, which seems a little odd because we've been focusing on everything we've done has involved factoring. Dividing polynomials really doesn't normally involve factoring. Now it could. There are times like if I were able to, we've actually done some polynomial division already when we cancel like factors. If the top factors and I have like the denominator is a factor of the top, well then yeah, I could cancel those, and that's a great idea. In this case, 3a is not a factor of the top for sure because this doesn't have an a, right? So we won't bother with that. But that is a good idea. I mean, if we can factor the top, and again, we can cancel the factor that's on the bottom, we just divide it, and that's great. We're going to focus on situations, though, where that's not an option, where the bottom is not a factor of the top. That's the kind of stuff we're going to work on today. If we're dividing by a monomial, we can do something pretty easy, right? Doesn't this look just exactly like a common denominator of 3a, right? Why not just split it up? Split up the common denominator into 3 separate fractions, and that's just what this is telling us up here. Here's our strategy if we divide by a monomial. Split up that denominator and make a bunch of small, simple fractions where we've got monomial divided by monomial. So for us, it would just look like that, right? The first term is a monomial. Divided by that monomial, that's pretty easy, right? Dividing monomials, all we have to do is simplify the numerical fraction. We reduce that fraction, and then just apply properties of exponents, right? So that makes it pretty simple. What are we going to get from our first term if I simplify?
Negative 4x squared.
Yeah, everybody agree? Because the fraction, the number part, is just going to simplify to negative 4, and a cubed over a is just a squared. Good. So we just get that. How about the next one? What's this simplify to?
12.
Yeah, 12. Look, the a's just cancel, don't they? And I just get 36 over 3, which is 12. And in this last one, what do the numbers simplify to?
5.
Okay, minus 5. Okay, gotcha, 5. And then what about the variables? Yeah, the a stays on the bottom, right? The a, there's nothing to cancel the a on the top, agreed? So we're just going to end up with that. Okay, no big deal. So again, the strategy we have if we're dividing a polynomial by a monomial is just break it up into separate fractions and simplify each one. Okay, piece of cake. That's not a big deal. Okay, what if we're dividing polynomials though? If you divide a polynomial by another polynomial, something that's not a monomial, then that's where long division comes into play, right? So let's remind ourselves, first of all, how this works. Let's just go through an example real quick without variables. Let's just review how we do long division. So what do we do here? Okay, right. So now let's talk through the whole thing. So we're going to start at the left, and we're going to pick the first number that's inside the division symbol, right? The first number that 43 goes into, and then we'll just do that small division problem. Well, 43 doesn't go into 7, so we got to go over one more digit. Does 43 go into 72?
Yes.
Yeah, how many times? Once. Okay, so then we get 1. Now what?
Subtract 43 by 7.
Okay, so whatever the number is, the digit that appeared on top, I'm going to multiply that by 43, right? And then what do I do? Subtract. Okay, everybody, right? Is this ringing a bell? You guys all know this process. We subtract and we get 29. Now what? Bring down the 5. And you could optionally, you could bring down the 5, or you could just bring down the whole number. It doesn't matter. Either one, right? Let's just bring down. Oh, is that not doing it? I do it over here. So we bring down the 5. And now what? Do what again?
Yeah, how many times does 43 go into 295?
Okay, how many times does 43 go into 295? What's the answer? 6. Okay. So then what?
And then
Multiply, good. And then subtract.
bring down the 6.
Okay. And et cetera. Right now we just repeat, is rinse and repeat, right? We just bring down the 6. 43 goes into that how many times? 8. Good. Multiply and subtract. Okay, now what?
Keep going. Add a 0.
Do we?
Add a 0.
Decimal point.
No, we don't add a 0.
Oh, remainder?
That's okay. You guys are thinking if you want to make a decimal. I got you. Yeah, we're not going to do that. We're going to leave this as an exact answer, because if we do this as a decimal, we might get an exact answer, or this might end up just repeating forever. We just always want to leave this as an exact answer, which is a fraction. So how do we turn this into a fraction? Exactly, because the remainder, everybody agrees this is the remainder, right? What is the remainder? Well, the remainder, just listen to this very carefully, because this really helps. If you remember this sentence, the remainder is what remains over the denominator, right? So the remainder is what remains over the denominator, which is what's inside, right? Or actually, what's out there, right? That's the denominator, okay? So we end up getting, our final answer then is going to be 168 plus 32 over 43. Now, we wrote this as a mixed number, which is, we don't really use mixed numbers anymore, right? But what does that mean as a mixed number? When we write stuff as a mixed number, remember, that does not mean we're multiplying. It means we're adding that fraction to the end, doesn't it? Everybody agree? Okay. Okay, so now let's take this process and let's apply this with polynomials, because it's going to be exactly the same thing. So in the previous example, what did we do? Our division technique is divide, multiply, subtract, bring down, repeat, right? Over and over and over again until finally we got to the point where we couldn't do it anymore, and then we just had a remainder, which we created a fraction out of, right? Okay, let's do the same thing with polynomials. So what do you think we're going to do?
How many times 7 plus 3 goes into 28?
Okay, yeah, so what are we dividing into what here? This is the part that's a little bit, this is a little different than just with numbers. Because with numbers, we would have said, how many times does this go into the first thing that it divides evenly into, right? Okay, but what we're going to do here with polynomials is we're only going to look at the leading terms. So how many times does the leading term outside divide into the leading term inside? That's equivalent to that first step where we're dividing the number by a number, right? Okay, so step 1, divide 7x into 28x squared. Again, only the leading terms, ignore the rest of it, right? So what's the answer? How many times does 7x divide into 28x squared? 4x. There you go, 4x, right? Everybody agree? 7 goes into 28 4 times, and x goes into x squared x times. So what do you think I do next? we're just going to follow that same process. We divide first, then what do we do? Multiply, okay? So whatever term we get on top, we're going to distribute that to the entire polynomial that's outside. Remember, that's the denominator, right? So we'll distribute that to the denominator. 4x times 7x is 28x squared, and 4x times 3 is 12x. Okay, good. Okay, now every time we do this, guaranteed, unless we made a big mistake, the leading terms will have to cancel, won't they? Because that's how we chose the 4x, right? We chose the 4x as what happens when we divide 28x squared by 7x. So therefore, we always know when we distribute, these two things are going to cancel every time, right? So then we subtract. So if we subtract, now there's a couple ways to show this. Okay, listen, you guys better be paying absolute attention. I feel like I've got 90% of the room is paying 100% attention, and then there's people that aren't. You better get this. You got to really pay attention because it's a process, right? So one way to do this is not actually the way I prefer, but it's okay. I mean, you can kind of decide which way works best for you. When we subtract vertically, is just put negative signs up above the symbols, right? Then you can keep track of what you've done. So I subtract here and I get 0. 23x minus positive 12x would be what?
Negative 35x.
Negative 35x. Good. Okay, good. So when we subtract, we get that. Now what do you suppose we do? Bring down the minus 15. There you go. Good. And when you're doing polynomials, honestly, what I would do every time is just bring down the whole thing. Okay, but that's not the way they're going to show it, but that's what I personally think is better to do. Okay, now we repeated one cycle, or we finished one cycle. Now what do we do?
Do we use the 3 then see how many times it go to the negative 35x now?
Okay, we always use the leading term. Good question. We always use the leading term. So now what do you think we do instead? Say it one more time. There you go. Okay, how many times does 7x, the leading term outside, divide into our new leading term inside? -5. Answer's -5. Okay, we got a new term on top, so what do? Okay, good. We multiply by the outside polynomial. We distribute. -5 times 7x is what? -5 times 7x is -35x, which we knew it had to be, right? Because it's got to be the same thing that we had here because they have to cancel. And then -5 times 3 gives me -15. Now what? Subtract. Yep. Subtract. Okay, so what do we do here? So when we have negative signs, subtracting, we just make a vertical line to turn those into pluses, right? So these cancel and those cancel. So what's that mean?
We're good.
We're good. We have no remainder in this case. So our answer then, with no remainder, our answer is just 4x minus 5. That's the simplified quotient. When we divide this big quadratic polynomial by this linear polynomial, that's what we get. Okay. So would factoring have worked here? What do you think?
No. Well,
Because what we just showed, here, let me take a picture of this. You guys understand my question?
yeah.
And this is stuff we'll talk more about later, but I think you probably can answer it right now.
Yeah, so the factor is just 7x plus 3 times 4x.
Okay, so what's this mean? Right, we wrote this using a division symbol, but if I write this as a fraction, isn't this the same thing as saying $28x squared minus 23x minus 15 divided by what? 7x plus 3 equals what? 4x minus 5. Okay, how could we, that's the same thing as 4x minus 5 over 1, right? So how could we write that as a product instead of a quotient? Like, what could I do to, like, I've got a proportion here, right? So I could cross multiply. Or I could clear fractions by multiplying each side by 7x plus 3. Everybody get that?
Yeah.
Okay. So then isn't this the same thing as saying 7x squared minus 23x minus 15 just equals what product? 4x minus 5 times what?
7x plus 3.
7x plus 3. Agree? Right? So would factoring have worked?
Yes.
It would have, wouldn't it? Right? Because look, everything that's in the top, you guys see this? Everything that's in the top, that factors, right? That just tells me right there that polynomial in the numerator is equal to the product of those two binomials, right? So yeah, if I factored this thing, it would just look like 4x minus 5 times the quantity 7x plus 3 divided by 7x plus 3. So yeah, factoring would have worked here, right? Would have worked. Those guys would cancel. And my final answer would just be 4x minus 5. Right? Give me thumbs on that. Does that make sense? Okay. But we didn't know that. Which one's quicker? I mean, I guess if you could see, if you got pretty good at factoring and you could see that I'm going to have that top thing is going to factor and I'm going to get a 7x plus 3, then maybe it's worth it. But practically speaking, I don't know. I mean, that's asking a lot. You run the risk if you factor this thing of going through the whole process and having it not work, right? Of not getting that factor in the numerator, that 7x plus 3, and then you still have to use long division. So practically speaking, it's probably better just to use long division, right? Just dive right into it. Okay, back to it. Let's try another one. How about this guy? Now you guys walk me through the steps. What am I doing first?
How many times is 2x?
Okay, 2x, divide 2x into 4x squared. What's the answer? 2x. Okay, now what? Multiply and subtract. Good. So distribute, subtract, and of course those leading terms cancel. What am I left with here? Negative 20x. I like it. Now what? Bring down the 8. Good. Okay. Now what?
Negative 10.
Okay, because I'm dividing 2x into negative 20x. Good. And that gives me negative 10. So I multiply and then subtract. Okay. Distribute the negative 10. I subtract. And what am I left with? 78. 78. Okay. So now what?
78.
Okay, that's my remainder. So what's my answer then?
2x minus 10.
Okay, 2x minus 10 is the polynomial part of my answer, but I had a remainder, so I'm going to have an extra term. I'm going to add to that plus my remainder, and my remainder is what remains over what? The denominator, which is 2x plus 7, right? So my final answer looks like that. Okay. Would factoring have worked here? It would not. What's the difference? This time, why would factoring not, the fact that I had a remainder, there you go. Okay, this is what we're gonna call, kind of end of the week-ish. Well, actually, probably Wednesday, we might get to it. Wednesday, we'll call that the remainder theorem, right? That's a really important thing in algebra. The remainder theorem tells us that if I divide polynomials and the remainder is 0, then that tells me, actually it's called the factor theorem, then that tells me that the denominator was a factor of the numerator. But if the remainder is not 0, as in this case, then 2x plus 7 is not a factor of the numerator, 4x squared minus 6x plus 8. Okay? Make sense? All right, one more. I just want to show you the alt. I think you guys just try this. Actually, let's go through one more together, and then I'll let you guys do one on the board. Okay, this is an important one, though, because there's something else here we got to talk about. So this time I'm dividing by a nonlinear denominator, right? The denominator is quadratic. It's got an x squared in it. Okay, so what am I going to do? I'm going to write out my division symbol, right? What goes inside? 3x cubed minus 8x squared plus 11. Okay, can anybody anticipate here, though, when I write that out, I have to be very careful and organized. What do I need to do when I write that out, do you suppose? Keeping in mind that we're going to go through this whole process of distributing and subtracting vertically.
Separate negative.
I don't have to do that explicitly, but there is one thing I have to be very careful about.
X squared versus the cube.
What do you mean by that? If I'm gonna now just kind of look forward here a little bit, let's just kind of play mental chess. We got to look a couple moves ahead. If I'm going to be subtracting stuff vertically, and all those examples we looked at, when we subtracted stuff vertically, they were they were simpler examples than this one in the sense that everything lined up well. What, you got an idea?
The one's gonna be just an X, right?
Yeah, okay, right. So I'm missing an X term. So what do I need to do?
No idea.
Well, okay, so you're onto something though. Say it again.
On the right track.
Well, okay, so when I subtract vertically, remember that it always worked out very conveniently, so I'm subtracting like terms vertically, right? Okay, well, I need to have the capacity to subtract x terms even though they don't appear in the numerator. So that means I've got to put a 0x term in there to carve out that column for subtracting. Everybody see that? So this is the way I need to write this. I need to have a column for every power of x inside the division symbol, right? That way when I distribute, I've always got a place to put each power of x so I can line them up vertically and subtract. Everybody get that? Okay? All right, so very, very important. Inside the division symbol, right? I can't remember what you call that thing. It's got some fancy math name, but I don't know what it is. The division symbol. Inside the division symbol, we've got to make sure that we have all powers of x represented. We establish a column for every power of x. I do not need to do that, even though our book does this, totally unnecessary. You don't need to do that outside, because when you distribute from up here, we're just always going to put the results in the correct columns. We don't have to have, like outside, I do not need to put x squared plus 0x minus 1. Do you get my point? That's not necessary because we're not subtracting out here. We're only subtracting inside the division symbol, right? Okay, so then outside we get x squared minus 1. And what do I do first? I get 3x, right? And the way we get that, remember, is this. I'm just doing leading term inside divided by leading term outside gives me 3x. Okay, so there it is. Okay, now what do? I got a term up here. Good. I distribute. Okay, so we're going to take this whole thing and just distribute over here. And what do we get? So I get 3x times x squared is 3x cubed. I had to be, right? Those always are the same. 3x times negative 1 is negative 3x. Where does that go?
It goes in 0.
Okay, it goes in the x column. Minus 3x. And now we're going to subtract vertically. Okay, what do we get?
-0.
Zero. Okay, now what about this guy?
Just bring it down.
Bring it down. Good, because I'm subtracting 0, so it comes straight down. 0x minus negative 3x. Positive 3x. And then I'll just bring, like I say, I just like to bring everything down each time. I just feel like it's cleaner if you do it that way. Okay. Start over. Now what do we do?
Take out an 8.
Negative 8. And the way,
And then
where I get that is leading term inside
I got close. I was on the right.
divided by leading term outside is negative 8, right? So, make sense? Okay, questions? If you have any questions, stop me and ask them. Okay, now what? Good. Distribute, good. Okay, so we distribute negative 8 times x squared is negative 8x squared. Negative 8 times negative 1, positive 8, right? And what do I do? Subtract the whole thing as a quantity in parentheses and just subtract vertically. Cancel. What do I do here? Bring it down. And 11 minus 8.
3. Oh, positive 3.
Okay. Okay, now what? Can I go further?
You can put it in a fraction and simplify it.
Good. I can't go further because look, now the power of x inside is less than the power of x outside. That's when I know I'm done, right? I'm done. So this becomes my remainder. So we're going to put that in a remainder box. Let's get used to that. I know the book doesn't do that. I want you doing that. It's really helpful to do. And you'll see why. Trust me, when we do synthetic division, you'll see why it helps this process match up with synthetic division better. So my final answer then is what?
3x minus 8 plus x squared.
Wait, no, that's a bit.
Wow.
It's 3x
Oh,
plus-
yeah.
3x plus 3 over x squared minus 1. Because again, what does the remainder do? That's what remains over the denominator. Exactly, right? So my final answer is just going to be the polynomial part, 3x minus 8 plus what remains over the denominator? The remainder. Okay. Okay, so you guys go try one of these. Go to the board, try that one. Hello? Yeah. Okay, what goes inside? Everybody up here, please. What goes inside?
Numerator.
So 4x to the 4th plus x cubed plus 6x squared.
Plus 0.
Okay, good. Plus 0x plus 0. You need to have a column from the degree of the top polynomial is 4, right? So I'm going to have powers of x all the way from x to the 4th down to the constant. Based on the degree of the polynomial in the numerator, how many columns are you going to have? So this is 4th degree. How many columns do I need? 5. How come?
Because there's 0.
Okay, good. It's always going to be the degree plus 1 because you have to have an extra column for the constant, right? Good. And then on the bottom, or outside, I've got this big thing. Now, you guys were probably thinking this was pretty mean to give you such a big denominator, but it actually was pretty nice, wasn't it?
Pretty
Right? The bigger the degree of the denominator, the fewer times you have to go through the process.
Do it, Archie. You're
Okay, so what's first term on the top? X, good, because 4x to the fourth divided by 4x cubed is x. So I'll put it over in the x column. Distribute, and I get 4x to the fourth plus x cubed plus 3x squared plus 5x. What do I do? Subtract. Okay, so is that good? Oops. Like that, is that good? I gotta have parentheses. Gotta have parentheses so I know that I'm gonna subtract each term individually vertically, right? And I know what I did. And we get, they cancel. 6x squared minus 3x squared. 0 minus 5x. And then just 0, right? Which I don't need to write this time because that's my remainder, isn't it? X squared is that's a smaller power of x than what I have outside, so I know it's the remainder, right? And so my final answer is pretty simple. It just looks like x plus my remainder over my original denominator. There it is. Okay, good. Work day tomorrow.